Hello, everyone, and welcome to the second installment of the Design Process Workshops. My name is David, and we'll be going over a bunch of the basics that is necessary for you to go about with executing a design and the project itself so that you can have a successful outcome. And this will be very quick based on terms of what I'll be unleashing onto all of you today, and for those watching later. It will be very in-depth, and then we'll actually go over live some examples of how to go about using these tools that I'll be explaining, and that way you can go ahead and start using them and trying it out yourself, so that way when you come and encounter a problem or you're developing a project, you can actually have a head start amongst your peers. So as a quick recap on today, we're going to recap from workshop 1, so that way we can all be on the same page here. And the first thing we're going to talk about or go over again is the origin or the legacy of a project. And what this entails is what the designers do, which is to designate, and that was based on those generational legacy problems again, where rational models are very objective intensive, or they rely on a lot of data. And then there's action-centric models, which are more of a creative refinement, kind of a lollygagged method to get about a solution, but it is still very critical because it relies more on the thinking and thought process of a designer rather than the objective quantifications or qualifications that are set in stone by, say, like an engineer. And these are typically what these models represent. Rational would typically be an engineer's model. Action-centric are typically like actual designer models. But for a great engineering designer or designer who loves engineering is to leverage both models, and that way to have a creative, objective refinement process to go about your design. That way you have this source of validity in your projects and goals. And that way, when you go about presenting it, you are able to justify those said projects and goals with your validation, which is really important. So the facets that kind of encompass design were interaction designs, mainly like a steering wheel, foot pedal. This could be a pencil. This could be the way you sit in your car and the audio responds to you through like a smart system. Industrial design is concerned with the scale, management, cost of a certain project, and that happens to mutually benefit the end consumer and as well as manufacturer. This is what's found prevalently in a bunch of the big tech companies are like FANG, if you are into stocks. The experience facet is more along the lines of what can we do to have people engaged more thoroughly. And this is more equipped into like, having a night market kind of experience, virtual reality, augmented reality. Those are experiences that we have. Virtual classes are an experience. And so human-centered design is another facet which is concerned with the behaviors and the tendencies of a person or a human as a priority designation for a outstanding or outcome of a goal. And so what that does is it places, how does the hand, actually grab something? What are the mechanisms that are involved with your extremities to make sure when you grip a handle, you're not feeling, like you're going to get arthritis. There's not going to be any tendonitis that develops later. And so these are some of the goals of the bigger companies, and also as well as the entire facet itself of human-centered design. To go back into the mindset, just remember to keep these 4 things in mind: is that design will never be linear. It'll always have objectives or processes that may take you tangent, but it is the job of the designer or the engineer or the project manager to make sure that track is as linear as possible. Every designer has a great vision. If you can't see or perceive or create something that's not there or something that people want to use, you also have to work that much harder to try and define that, which may lead to some problems downstream. So having a vision is very key for a designer in terms of your mindset as well. And as well as the consequences from decisions. Those consequences can evolve. They can also manifest or snowball. And so you want to make sure that when you make a compromise or a trade-off, you're also evaluating what you gain and what you lose at every step. That way, you know what the actual end goal might be, so that when you do go about justifying these design critiques, for example, you're not kind of just saying, I did this because it looked pretty. I did this because X, Y, and Z, and that way I can have a more, competent appeal. Execution is probably the greatest thing that must occur for a designer, and in their mindset, because if they don't have a plan to execute, it'll only almost always lead to where the problem never gets solved, or you'll go about in a cycle where, or this loop where you're stuck and you have to figure out how to get out of there. If you have a plan to execute from the beginning, you're much better off. And this is from Don Norman's the book, The Design of Everyday Things. There is one thing he states in there from multiple studies that are done in the psychological world, which is that you need to strike a balance between a mindset that's positive and a mindset that's negative, which sounds counterintuitive. But the reality is that if you have a positive mindset, this is where your creative kind of bubbles or purges begin to really form or fruition themselves. And this is where it's great for ideation, getting ideas off the mind. What are our possibilities? Answering that question. And then he states that having a negative mindset is something that's more anxious driven, that has more of a deadline to it. And what this is to kind of keep you on track when going about a certain process. And to have both work really well, you can't fall on the extremes of either, because then you'll fall into this rabbit hole of where, oh, this is so creative, I have 1,000 ideas, cool, but that 1,000 ideas came at a cost of 10 weeks, as opposed to getting out 100 ideas in 2 weeks and then moving forward from that. And the really opposite extreme for really negative mindset is like, if I'm so enamored with making these decisions that I can't see anything past it, or I have developed a tunnel vision for design, that can also be very harmful to what you're trying to execute in an overall scheme of everything. And so Don Norman says to have a balance of both, but to not have too much of either. So that's the main takeaway there. And again, humans have these two conscious systems of cognition, or subconscious, unconscious. And again, subconscious is fast, innate, inherent. It's a visceral behavioral response, whereas conscious is a more reflective response. And this is where, conscious comes from like doing homework. That's where a lot of conscious time is taken up. Subconscious is when like I want to go take a walk, or if I'm talking to someone at a table. Those are subconscious actions taking over that you don't even have to physically think about. And so again, we talked about levels of processing, which is visceral, behavioral, and reflective. Those are the 3 levels that are engaged with these 6 steps or 7 stages of action. And 7 stages are from the world, which is to perceive, interpret, and compare, whereas the goal is to plan, specify, and then perform, going into the world. And so these levels of processing is consistent throughout all human beings. And so designers, we make these choices about from the goal into the world, and then from the world we receive to derive a end goal. That's very important. And for the next part is the actual design process that I want to reflect over. And this will grow indefinitely, and just be worried that this design process that you see the figure here on the right is actually a subset of steps that happens along the entire process. So if we had a linear scale from beginning to end, that iterative kind of cycle or loop will happen more than once between each steps. And it can happen, and this is where the hard part is where how do we define when we cut or stop making those loops, and then we have to actually break into a solution. And so that's what we'll be going over more in depth today. Cool. So as I was trying to bring up, we have these methodologies that we use. Design thinking is more geared for ill-defined problems, things that we aren't necessarily comfortable with or we have very little research for. Agile thinking is sort of something where we are very knowledgeable or extensive about a certain topic, and we're really just trying to push out a product for a need, for a customer, for a personal private interest. And systems thinking kind of takes that entire encompassing scope of view and kind of looks at how what process or what steps needs to be taken and what are the parameters that we measure for those steps or processes to say, yes, we can improve, or yes, this is viable for the team or for the system as well. And so just to reiterate, the design thinking is to apply critical and creative thinking to understand, visualize, and describe complex, ill-defined problems. Agile is a method for breaking tasks into small increments with minimal planning that do not directly involve long-term planning. And then systems is problem solving by viewing problems as part of an overall system, rather than reacting to a specific part, outcome, or event, and potentially contributing to further development of unintended consequences. And yes, so one of those tools that we use to say, how do we know what goals to set for ourselves? We use a SWOT analysis tool. Again, just to set a number with real deadlines, make sure we can actually measure it. Is it realistic or attainable? And those attainable and realistic are interchangeable. And time bound is just setting that deadline for us, or making sure we can't infinitely work on a certain task because we'd get nowhere. And then there's the diamond model we briefly went over as well. And what the diamond model is to show how you would go about from a research point of view or defining the problem, and then diverging into understanding what is that problem. Then we converge to define that problem. And then once we have some insights as to what that problem and research has led us to do, then we go and look forward into the next diamond, which is about prototyping or reiterating. So the agile model works well or agile methodology works well with this model because they both kind of are interrelated. But again, they aren't mutually exclusive. So just keep in mind that you can use any tool and leverage it in any way possible as long as it's coherent. And essentially, we want to push out an end product. For the last thing we went over last time, and I went very brief into this, which was a QFD. And what a QFD is, a quality functional deployment tool. And what this does, it defines the high-level overview of our needs or problem sets or requirements related from the customer, public, or private interest. And then we set those design goals or standards, which is the columns. So the customer requirements are the rows, the columns are the problems we're trying to solve for those requirements. And they can look either very identical, where they have just a diagonal line, which is what the ideal kind of customer requirements matrix looks like, but some typical requirements don't follow a diagonal line between the rows and columns. They can either have like 2 columns full with our rows full. So it can look like anything from everything in the columns has an X for a certain requirement, or it can only have 1. And we'll go over more in depth on this in a future workshop. So as a quick open discussion, was there anything you found interesting from the first workshop or from one I went over? And was there anything that you found to have a hard time understanding at all, or anyone?
I was, so is the QFD that on the previous slide, would that matrix be applicable to any of the design methodologies?
Yeah, so essentially QFD is what you use to derive after you've gone through a charter. So you have a charter, which is where you do your time, scale, and cost.
Like a GANTT chart, per se?
That's exactly what a GANTT chart is. You're on the money with that. But then when you actually get into the designation of how do we go from an idea to a real thing in real life, and then how do we get there? So how do we bridge that gap? And that gap is the QFD relationship that follows from idea to real life product. So QFD is essentially applicable to all methodologies. QFD is more of just a tool within each of those methodologies to accomplish. But it may not be, it's applicable to design thinking, agile methodology, and as well as systems. Right, like this is an entire system of a product essentially with this QFD relationship. And it's I don't want to narrow your tunnels. You definitely want to keep it open. So yeah.
So like this could be applied at a lot of different scales for
Exactly.
whatever the specific project is.
Yep, that is completely correct. And these, like I was saying in the first workshop, is that these matrices can be 5 by 5. They can be a 10 by 10. They can be like a 10 by 20. You know, like we have very, general customer requirements, but the design requirements to achieve those are like 20 columns deep for us to achieve those customer requirements. So.
And so with the columns, would the entries be like a scale? So similar to like a decision-making matrix kind of thing?
Yes, so exactly, that's it. So every time you have so you see a matrix from left to right, and each one of those values inside the columns of that matrix. So for the first one, which is the requirements matrix, you have design requirements, and those are assigned a weighting factor or that scale that you define. And typically that scale can be from 1 to 10 or 1 to 5. The key thing is though, and I'll mention this later, is that if you have a scale of 5 applied to your first matrix, you want to keep that scale within each matrix. So you can't assign more than a scale of 5 for each column that you see for each matrix. And so if I say like my requirements matrix has a scale of 5 for its design requirements, but then I move over to the engineering matrix or design matrix, and I have my engineering design requirements, and then I make that out of a scale of 10, you've then broken your relationship between the matrices because the scales that they're defined upon or linearized is not consistent between each matrix. So if I start with 5 at the very frontmost matrix, then I will end with a scale of 5 for quantitatively defining it at the end, at the control verification matrix. Yeah, that's a very good question.
Yeah, that seems like a really useful tool to kind of see how a design decision is just traced all the way through to a final product.
Yep, and the key thing is to make sure those scales are consistent, otherwise the relationship breaks.
Yeah, thank you.
No problem. Liz, do you have any questions or things you want to talk about that you'd like more clarification for?
Yeah, I've never seen the diamond model before. I've seen QFD and SMART goals, but this is like the least linear image.
Yeah, so the diamond model it's a very extrapolated and abstract tool, and what it's meant to do is to generate. So this tool is meant to help you generate possibilities and then also selecting those possibilities. And you may not always have just one end like selection, you may have 5. And then after you have 5 that you selected, you use a tool called DMMs or a decision-making matrix to tell you which of those best 5s is the best option to move forward with. So you have times where you have to expand to see what's available because again, you want to exhaust any and all ideas for you to come at the best one. And then sometimes those ideas may, become hybrids of each other. And so that becomes, you have 2 ideas and you turn that into a hybrid and that becomes its own idea. And then, you kill those 2 ideas because those 2 together work better, etc. Or you can have 5 separate ones that have no relationship or are not mutually exclusive. And it can be to a point where you then have to find the goals from there. But essentially the platform design model allows you to generate and evaluate or select rather, and then use another tool in between the mediaries. So at the PS or the problem statement or at the UI or at the US kind of symbols in this slide here, those are the points where you use a tool, say like a DMM or a problem structure or a morphological chart, a QFD relationship kind of. And this is at those points is where you assess which solution or which idea or possibility is the best one to move forward with.
Okay.
Yep. Anything else? Cool. All right. So without further ado, let's actually talk about the tools we'll be using to go about our project planning and management. So the a few things is that slight overview is that we'll be going over a typical nomenclature, or what you'll be kind of exposed to in terms of terms, so that way I don't lose you along the way. We'll also be having a quick like an engineer perspective overview of what it looks like to design, and as well as some things to keep in mind, how to charter a project, which is using those morphological charts, problem trees, decision trees, DMMs, evaluating scope and scale. And then we'll actually go into how like SWOT and SMART are are intertwined with those tools as well. And then how we define those relationships. And then eventually, how do we say, hey, what we've conjured or what this team has developed in terms of what we want to propose, how do we get people to say, give us money, or say, we want you to fund this to back our ideas. And this is kind of a segue into workshop 3, where we'll be talking about public speaking and presentation. So we'll get a brief taste of that here today as well. And then at the very end of this entire workshop, we'll be doing about 3 or 4 live demos, which will be how to do a scope and scale evaluation, how to do a problem structure, how to do a decision tree, and then how to use a DMM. So we'll be going over those 4 things, and then we can go on to any questions or for anything that we talk about after that. So as I was saying, nomenclature that we have here, and this is typically what you'll see for any design process, really. And to start it off is something called an engineering V. This is actually a illustrated representation of what the typical design flow of an engineering product or prototype and its requirements are for throughout any step of a design flow or design process. We have a charter. So charter is namely the establishing or identification through research, market analysis, and the need that has been defined, which is a scope or scale from the customer or from a public or private interest. Another we'll be using a lot, which is called synthesis. And design synthesis is involved with brainstorming, which is the double diamond model in a sense, and purging those ideas and expanding possibilities, but also making a sense of, okay, we have all these ideas, we best not lose them. So let's make sure we document throughout the process. And this documentation is critical throughout the entire project, because then you have a say like, oh, this is what it looked like before, this is what it looked like at this step, and this is what it looked like after. And also it gives you a chronological way to say how your project evolved. And so that when people from the outside come and look at your project, you're like, yeah, so this is how it looked like through phase 1, this is how it looked like through phase 2. And then this is some shortfalls that we had intended for the project. And then this is what ended up looking like at the end of phase 3, so on and so forth. Again, it helps you with your justification, validation of a project and why you chose certain directions or decisions. And then in the industry, these are very well known. I've heard this, I've heard this repeated so many times at my old job. And this is such things are frameworks or philosophies, which is known as the Toyota production system. There's also something called life cycle assessment, and there's also something called human interaction design. To kind of give you an example of what Toyota production system involves, they use something called lean manufacturing, or quote unquote, just in time. And so what that means is that at every step within the manufacturing process, time and production are focused on providing what's necessary, specifically at that step and point in time, and that's repeated. So if I say I have this product from the start line to the end line, at step 1, I want to make sure it has components A through C arrive there just as step 1 starts. And then when step 1 is about to finish, step 2 is already getting its steps, or its parts D through F ready for the next step, so that when the product arrives at the next step, D, E, and F can be installed on that product. And that, we essentially had just-in-time manufacturing occur for that product in a specific step. And it's a just-in-time philosophy. There is something called achieves an ISO standard. An ISO standard is like a 9001 standard is basically a criteria for quality management. There's also another term that you've probably heard before, like Kaizen, Kaizen, and really that just means continuous improvement. And again, I don't want to overwhelm you, so these terms are more or less speech or kind of the vocabulary that's involved with investors. And so don't feel the need to say these things, but if you're trying to go and propose these ideas to investors, if you say these kind of key words, quote unquote, you'll have a better time of appealing to them, and as well as selling what you're trying to sell, the idea you're trying to market. And there are many interrelated tools that are used along the way, like Six Sigma, which is a tool to improve capability and statistical. It's a tool to improve capability. So we have something like statistical process control. You have control charts, or you have a failure mode and effect analysis. And you also have process mapping, which is basically like a block diagram with arrows pointing from one box to the next. And then we have something heard as well called 5S, which is an industrial term. And it's based in the Toyota production system, and it's meant to sort, set in order, shine, standardize, and sustain. And TPS, as defined from their Japanese heritage. So they have three constructs within TPS. The first one is called MURI, or MURI, and that is to not overburden a certain step. MURA is to limit or minimize inconsistencies between steps. And MUDA is the third construct within the proverbial Japanese philosophy, and that is to eliminate waste. So at each step, or throughout the process of just-in-time or lean manufacturing, you want to not overburden each step. You want to make sure that inconsistencies are minimized, and you want to eliminate waste, and that can be time or component or money. And so those are the kind of the three constructs of the Japanese philosophy for the Toyota production system. And so it's very important to know what they are in an industrial sense, so that when people say it, you don't just like, oh, what does that even mean? You now have a kind of a financial or investor kind of backing to say, oh, I know what 5S means now when they say this. So that's some brief nomenclature introduction for you all. And so here's that engineering V, which is a typical design cycle. So you start by setting the overall goals, then you go into requirements, and then you move forward into design. And then when you go into manufacturing, that's the kind of the tipping point or converging point to where you then diverge again. And so at assembly, you then are validating your design, and at the next step of testing, you're validating your requirements, and then at competition, you're then validating the outcome of your overall goals. So basically at overall goals and competition, those are your highest level objectives. And then your next level objectives, you have requirements and testing, and then design and assembly is another subset of requirements in terms of hierarchy. And then manufacturing is the pivot point within the engineering V process. And then to, I guess, keep it less verbose, is that validation is the act or process or instance of being well-grounded or justifiable. And engineering V kind of ensures that my design is then validated by assembly. Again, my requirements are then validated by testing, and so on and so forth. And this is just a very crude example. I mean, you can go very stupid in depth with how much you can do at every point. So, but some things to keep in mind for you all is that refinements are integral to the process of designing, and is critical for designers and their designs. Whenever you put yourself out there in general, for point number 2, which is similar to social media, right? A design is essentially an extension of you that is made public and vulnerable. Someone will always have something to say, and it is within a designer's demeanor to accept all criticism and act accordingly, but to never lose composure. This is the key thing, is because when someone says something negative about a design, don't get so enamored with what they had said. Instead, just take it in and be ready for what the next thing is that's going to be taken in. That way you don't get like fixated. Fixation is the pitfall of a designer, I would say. And it's also to make sure that you do not lose sight from less than desirable feedback. And the third point here is, which is made kind of notable or notorious within history by Benjamin Franklin. He said, if you fail to plan, you're planning to fail. So planning is key and it's critical, and it shouldn't be overlooked at any step of the way. And on the subject of quotes, some more that I would like to give you all as some sort of like rule of thumbs is that by David Kelly, he provided an axiom of design, which was fail faster to succeed sooner. So the more attempts that you have and where you fail, you then are essentially using the process of elimination to say what didn't work, so that you can then propose or go about things that will or may work after that. So you've exhausted all the non-possibilities, or that you thought were possibilities, to then say what else can we do from here. Another great quote is that any great design needs a pen and paper, and this is to serve as the instrumental basis throughout all aspects of the process. If you can, I guess, translate what you're thinking in a very ambiguous state, or a very ill-defined state, or open-ended state, where there's very poor constraints to define what your goal is, putting it on a pen and paper is probably the strongest utensil or strongest set of tools you have for designers, so that you can keep moving forward in your design. And as I mentioned earlier, documentation is critical. Be sure to document. This is by taking pictures, doing renders, using a design log, using whiteboard sessions and taking pictures of it. This is in meetings and minutes, where you have someone take minutes while you're running a meeting, using MS Paint and screenshots, using problem trees, QFD relationships and matrices, and in-progress updates of sub-projects are also very critical for documentation. That way, along the way, you can keep track of what you've done and what you still have left to do. Kind of that, I guess, that transition for designers. And so documentation is very key. And moving forward to my next slide, I want to bring back the, move forward a slide. So the initial project charter, again, this could be a very ill-defined or open-ended problem. Rough time estimates will be okay, because this project charter will develop over the course of your project's timeline. So you will have an idea of what it looks like before the project starts, and then as the project is ongoing, this charter will then expand to make sure that it allocates and is encompassing all the problems that may arrive, or from certain teammates, or certain unexpected phenomenons, like a tornado hitting someone's house and that just wipes out their internet, kind of deal. Like the list goes on. This is something called like a contingency plan. So that's something we'll be talking about later too. And so initial estimation will then be impacted by the problem, or which could be internal or external. And initial project charting, it's just a matter of time bounding the project. You just want to set limits and you want to appeal to them, and then you then have that kind of validation is during the actual project itself, and saying, okay, did I meet this deadline? Why not? Okay, I had to take an extra 2 weeks to complete this step within the project. And that's something you evaluate at the end. It's like, why do we take 2 more weeks? Right, make sure you document those things, because then you can actually say and assess, going backwards, how you can improve your project planning and management. And so the next few slides will be used to discuss the charting of a project. It is entirely dependent on the problem you're solving. And again, methodologies or tools will overlap or intertwine. And it's understanding of when to use the appropriate methodology or tool to solve the problem. So let's first evaluate the scope and scale of the project when you're planning to draft a Gantt chart. So again, we have design thinking. And design thinking is very a highly reflective processing design methodology. And because you have a what is map, and I don't, yeah. So you have your design or visualize here and brainstorm, but you can see that these three triangles here is where you'll know that this is where a majority of your time will take place, because this is where majority of the steps and processes are. Just like for agile design, a majority of the time will be spent here during iterations and the release endgame. And system thinking kind of has an even amount distributed because it, again, accounts for the entire system, not just for a specific prototype or process or objective or goal. Systems thinking is, again, infatuated with how does the system work and interoperable and its interoperability. And so you'll be seeing these kind of transformations of these methodologies in the next few slides. So going forward, here we have a typical, I guess, more, if we zoom in on the scope a bit from the initial design problem or process tree that we showed earlier. And this is telling us when we have an overall problem, we want to clarify objectives, establish functions, set requirements, which then determine sub-problems from those requirements and determining those characteristics of the sub-problems, generating those alternatives, and as well as that relationship of these 7 stages of actions, which is from the world and to the designer, and then from the designer to the world. You have these generating alternatives, you can evaluate those alternatives, improve on details, overall solution, and then you can go back to the overall problem to see or assess how did I, what was my end result from this whole process. So this is just another picture or visual for you to enjoy. The next thing I want to bring up, though, is scale and scope and its analogy. So scale is primarily defined, or not defined, but I guess primarily involved with the time, cost, priority, and the magnitude of it. And so this relationship with Matryoshka dolls is that you have one doll would encapsulate the next as it goes into the kind of succeeding doll. And then the scope is representative within each doll, as to say one cannot be nested within the other if it doesn't fit. And so you're going to have things that fit your scope and scale, but they won't necessarily always fit at the right time, or it's finding the appropriation of that certain step or process within a project to say this is real, this is doable, and this is applicable. So the purpose is to be able to accomplish everything or encapsulate everything. The difficult consideration would be the time, the cost, and the priority. Again, the triple constraint of any project, and especially since those considerations comprises the end result. For competent planning of project tasks and dependencies, let's then familiarize ourselves with another interpretation of the Matryoshka dolls. And so here we have kind of a linear scale, and this large arrow from left to right across the screen with my pointer is a time, and this will always more than likely be time. All right, and so you have these arrows for scale, and you have arrows for scope, which are in this like kind of turquoise blue. And so you can obviously see that the arrows of the scale are pointing to kind of like the boundaries within a certain project or a task. So these big circles, they all represent a certain step in the process. So let's say like our first step here, which is the first circle, takes up this amount of time, it has this much priority, and has this much cost. That's what is inside this circle, and that is the scope. And just like in this circle at this second step, right? And here we notice something interesting. At this second step, we have this transitional point, or this interjection between the steps that overlap. And what this tells us is that between from step 1 to step 2 and step 3, there is some overlap that must be considered for this for this process to continue forward. And it could be an evaluation of the scope within each of these kind of domains of the circle. And we'll be going over a live example in the end of this presentation. But I want to kind of keep your guys open to the mindset that how you define your scale and scope is completely dependent on how you perceive it as a designer. So here we're using circles. You could be using a hexagon. You could be using a square, or like a rotated square, which is a diamond essentially. And I don't want to kind of tunnel vision you into thinking we only use circles. And so it basically just I want to emphasize the difference between scale and scope, and also why they're interrelated. And so we have, excuse me, now we have the condition of what comes first, right? Does scale come first or does scope come first? In essence, both must occur at an equal amount or within equal opportunity to work well together. And which this means they're not mutually exclusive. If there is an afterthought in the design project itself or the design project and its planning, it will present itself later on or downstream in the project itself. And so coherence requires the mutual inclusivity between scale and scope for you to achieve a successful outcome. And so this is just a kind of a brief and very abstract way to kind of visualize scale and scope. Now, we're going to then be talking about what are the words that define said scale and scope. Cool. And so we have very general terms, right, which is like manufacturability. We have cost effective. We have simplicity, packaging, and time. And these are like your design requirements, right, that we said were in the columns of your QFD matrices, right? Or these could be the customer needs that are in the rows of your design requirements matrix. And then, so from left to right, we go from general to specific. And the general is where we are at what the customer wants, right? They may not know what they want, like an ill-defined problem. They may have an idea of what the outcome is. And so that's great, but it's also kind of harmful in a sense for a designer, because you're then using what the customer has told you is the problem to define your problem that you're trying to accomplish or you're trying to solve. And so that may lead into some kind of mixed interpretations. And so it's best for the designer or design team to look at the general scope and scale that the customer wants from you. And then how do you derive that in terms of the product itself, not what the customer wants. So it's a very duplicit method of thinking, but it can be a pitfall or it can be a great benefit. So it's measuring what the customer needs, how do we evaluate that, and then these are measurable methods to say, hey, we can measure this to make sure the customer gets this manufactured in source of time. It doesn't require this type of method of manufacturing. When the customer said they wanted to be sold at a very low price and be competitive, this is how we're going to do it with being cost effective with X, Y, and Z. They wanted something simple, et cetera, et cetera. And so from left is the more customer based requirements and needs. And then if we move on to the right, we have something like viability, efficiency, coherency. It's like, how do we define simplicity? Well, it requires efficiency and coherency, and it has to be viable, but it could also not require complexity. And for packaging, we want to make sure that it's efficient. We want to make sure it's lightweight. So we have like packaging going to, if you can imagine an arrow going from packaging to efficiency, packaging going to lightweight, packaging going to coherency. And so you can kind of see how these kind of grow as they go down to be more specific objectives for tasks. And so this is where you then get to see the more tasks I have, the greater my scale and scope will be as well. And so as you get more specific, your scale and scope increases, but at a general level, it's very straightforward. And this was, as I presented earlier, like the changes in the scale and scope of these circles here. And you also have some of those exhaustions of specific goals or objectives. So say right here at step 3, which is this really big circle, right? So we know that this outline here, that it kind of cuts off that 3rd step right here. This is our entire project scale and scope. This is what we're allotted by the customer. If we go outside of that bound, like what step 3 does here, so this bound here, or this area, would be seen or deemed non-feasible to pursue when going about your scope and scale, because it is outside your scale and scope. So you as a designer define your scale and scope, and then if anything crosses the boundary that is outside of your scale and scope for the entire project, you should not execute those things or evaluate or explore those possibilities in any greater detail or depth. And so that's why we have this kind of analogy here. And that's how you know that whether or not what you're choosing for determining your project and its specificity, whether it's feasible or not. So that's a very estimational way to do it. There's been no quantification here. There's been no qualifications here. It's just that what we think will happen in each step, and what we assume to be the length or time scale or complexity scale or budget scale for each step. And so that takes us into a Gantt chart. And a Gantt chart is a very linearized method to kind of focus. And this is, again, more for investors. This isn't necessarily how it is reflected for an engineer or designer. This is more to say, hey, investors, these are the steps that we need to do in order to complete what you required from us. We're following this here from now on, and any stipulations that you want to, throw in there, you have some changes you want to make. This is your cutoff date. This is your cutoff, time. We will no longer accept any changes in scope after this point. If you want to have a different end goal, then we will have to do an entire new project. And so from here, you can see on this Gantt chart, we had 3 phases. So phase 1, phase 2, and phase 3. They all had equal amount of weeks in them, which is 12. And within those 12 weeks, we then broke those up into how the project were to be coerced or coaxed. And in the beginning, it's very document heavy, very research intensive, brainstorming intensive. And then phase 2 is very much, how do we get these ideas to a prototype? And then phase 3 is when we're ready and setting it for presentation or delivering it to the customer. And so you can see that phase 2 and phase 3, or phase 2 rather, has probably the biggest gap because it took up the most amount of time. And it has a bunch of deadlines. And then we had markers on the top, which is this little deadline kind of window here. Let's say what deadlines we're approaching on these specific days. So these are just key markers. Again, you don't have to use this tool. This is just a way for you to pass on to an investor to say, this is what we expect to do in this amount of time. And so you're more than fair enough to tell them, this is out of scope, this is out of scale, we don't want to do this, or we think that if we do add this into our scope, we then have to cut a project in order for us to achieve this project. So there has to be, again, a compromise or a trade-off. So definitely you're bounded by the 36 weeks, or 37 weeks it looks. Yeah, 37 weeks or 36 weeks. And so within those 36 weeks, what's realistic? Again, that's where SMART comes into play. That's where SWOT comes into play. And that's how you determine whether or not, what's a priority for something. And so I want to introduce you to all something called a problem tree or problem mapping. And this is a quick and efficient method to identify, project, and estimate time tasks for a certain project and sub-project or aspect thereof. And this is an example for a housing design problem. And what that is what kind of roof do we want, or what kind of design for the house we want. And in the middle, we have this kind of pentagon. And this is essentially all the major problems with designing a house. So in the middle of this pentagon here, you would have a word called house. And then what encompasses the house are those nodes, which is this circle here, this circle, this circle, this circle. And those are your directionalities of problems that could occur within a design. And so this is how you map the need with your problems that arise from that need, and then you can then derive more problems from the initial sets of problems in that pentagon. So as another way to put it, you basically want to take the need that you want, put it within the middle of that pentagon. Then with those 5 nodes or 7 nodes or infinite amount of nodes, you want to define the main problems that you want to accomplish or find the solution to. And then from those problems, you then draw a line to say the roof will have this type. And if we have this type, we need to worry about drainage and cladding materials, right? If we were thinking about external walls, do we have to then think about elevation? If we have a first floor, we have a direction of span, we then have to then think about the materials that are kind of interchanged with the first floor. Then we have the core partitions. How do we break up the ground floor? That's also a problem. And then the core partitions for the first floor or the second floor. And then, as you can see, it's just to basically, if I have a problem here, or if I have a need here, what are the problems that surround it? And can I define those problems into more specific things? And you don't have to get too intense because, again, this is just for project estimation. And then we assign, and then if you want to get really crafty, within these nodes, you have this link or a line. We can then assign these links to have is if you have, right, a vector is something that has direction or magnitude. You then say at this length of this problem, it will take 4 weeks. So if I have something that's 4 weeks and it's this long, that's how long that problem would take to accomplish or find a solution to. So for example, like internal walls and elevations, I think that's like a 2-week problem. I then shorten the length of that mapping from the node of external walls to the node of elevations. I think it's only going to take 2 weeks. So I then make my vector 2 weeks between that problem and finding the solution. Does that kind of make sense? Yeah, cool. And then essentially, when you get to a point where you have to kind of come back to this and revisit it, you want to write down your main idea or goal you're trying to accomplish, and then all that pre-researched or then research ideations or brainstormings that you have from your peers or from external resources, and then based on your specific understanding and your interpretation of the problem or focus, you will then purge of this as it expands and grows. So again, this is the diverging of a problem. Like this is very crude and very rudimentary. Like this problem structure could be like 30 nodes deep, you know, and like each node that you expand to could have 5 surrounding nodes that it has to be solved for that problem. And then each link between a node is the time scale. And then the number of nodes within a cluster is like the cost or priority that must be evaluated for you to achieve that need or solution to the problem. So again, scale is how wide and the magnitude of it or the length of it, and scope is what it takes to accomplish that or the transition between a certain project, objective, or task. So without further ado, let's move forward into using a SWOT analysis. Cool. And really what this is to, again, determine your strengths of the company or the product. You also want to define the weakness of the company or the product, so on and so forth for opportunities and threats. Excuse me. And so in essence, when you want to combine a problem tree and SWOT analysis together, typically this is what it looks like in a 2x2 table. And so you have your strengths, which is again, existing brand, customer base, or distribution, or product. And then you have opportunities, which is on the left-hand side, or in the rows. So opportunities in the first row, threats is in the third row, and then strength and weaknesses is in the second and third column. And we have where these kind of rows and columns meet, which is SO or WO, or an ST and WT, which means we have a strength and opportunity strategy and a strength and threat strategy, weakness and opportunity strategy, and the weakness and threat strategy. And again, this was a great picture that I found, and it's basically saying for S and O, we want to say that's our attacking strategy. For a strong threat, that's what's going to be our defensive strategy. And for weaknesses, is what we're going to build for the attacking strategy, or the strengths we're going to, or the weaknesses we build upon for the attacking strategy. WT is the opposite to that, which is to build strengths for the defensive strategy, or building upon the weaknesses for the defensive strategy. And so when you get into the point of a problem structure, you then have each problem, and that could then be defined by a SWOT analysis. So at each node that we had, for example, here, why am I delaying so much? Cool. So we have all these nodes here, and at each node, say like at either drainage or external walls, we perform a SWOT at, say, external walls, or external walls and roof or drainage. And we say for the roof, or for the drainage rather, we have a strength of, it's made out of this material, it should empty about this much liters per minute. The weakness of it is that it will corrode under the certain environment, and it may fatigue after 10 years. So its life cycle is ended after 10 years. Some opportunities would be for it to, how do we brand it? How do we find the right market? You know, do we go to the Pacific Northwest where they have a lot of rain typically? You know, we typically wouldn't go for a more less rain intensive state or region. So our product wouldn't sell very well there. And then for threats, we can see like what are the competitive businesses that are in the same markets as us, or say like another FSAE team who's also doing electric vehicles. You know, what is their threat to us? We also may have external or internal things. So external threats could be, you know, budget cuts. It could be member dislocations. It could be someone's working too many jobs. You know, an opportunity for VMS would be leveraging students and building teams. Another opportunity is to make sure we are successful in virtual activities. And what are some of the strengths and weaknesses of VMS? You know, we're really strong in the sense that we're here to be multidisciplinary, and we're very helpful and cordial with each other. You know, we have weaknesses to where we don't always have a business and PR system that's always working coherently. You know, another weakness of VMS is where communication could be improved. That, you know, that's a weakness. So it's all about how you perceive them and what you're interpreting, and making sure that they make sense when putting them into a SWOT analysis. And it's a useful method, because then you're now evaluating your problems. So this gives you a first step into quantifying or qualitatively defining them. And we'll get more into that in a bit. And so I just want to show you all what another problem tree or mapping could look like.
I'm going to pop out into my one of my class lectures that's just starting. Cool. I'll catch the recording once it's uploaded.
All right, sounds cool, Oliver. I'll see you later, though. All right, and so we have another problem tree mapping here, and this is to say we want to find a reliable and simple testing device, right? We want to make sure it has these features, or by what it's defined by the customer, which is your first level, which is, you know, between reliable operation, high safety, and simple production. This is what the customer wants, right? They want a reliable operation, they want high safety, and simple production. And so I think one trend that you'll notice here is that when the customer says, I want reliable or simple, that's literally what is translated at the first level for design. So they want reliable, okay, reliable operation. They want a simple testing device, simple production. And so you can see how the QFD relationship starts to trickle down, because it's literally given to us by the customer, or what we perceive what the customer has told us, to say, this is, in terms of reliability, this is what they want, which is operation. So we take that a step further, and when we specify the problems a bit more, right, we want to make sure that, so when we define reliable operation, how you define reliable operation? Well, that means, typically would mean a good reproducibility of torque time curve. This is for a specific device. And we also care about the tolerance of overloading, because then we kind of skew into the scale of plus or minus, which is what we don't want to have when we're measuring sensors. We want to make sure we're like plus or minus in the zeros, or 0% rather. And for simple production, that we want to ensure that the component is simple to produce and it's also simple to assemble. And then when we get to the next hierarchy, which is the engineering design requirements, right? To make it a simple component production, that means it must have a small number of components. The components must have low complexity, and that a simple component must have many standard and bought out parts. For example, going back to reliability, the testing device must have a low wear of moving parts, must have a low susceptibility to vibrations, and it must have few disturbing factors or external factors. And so this is how we can also map a problem tree. We're using SWOT analysis. Kind of SWOT is like, here's the things that could go wrong, which is the threats. And then these are things where we could go right, which is the opportunities. And yeah, so on and so forth. So the next structure I want to bring up, and this is a little bit much more overwhelming in my sense, because you have functional structures, which is essentially what a certain specific component or process or step and what it's meant to do. And you can see that we have like a near front wheel. So we have a carrying or fastening device that we want to solve for product. And we have here that the P, if a line is assigned a P, that is a problem. If it is assigned a D, it has been a decision or a made decision. And A's are the alternatives. So we have our initial problem. We have two solutions, which is to have the carry fastening device near the front wheel or near the back wheel. And you'll also notice that at each kind of step, we have a time has been assigned to it. And this is essentially, again, as this is more of a function structure that has been evaluated for a project that has gone on for a decent amount of time. But this is how in depth it can get for defining problems and functions, how to solve about those problems or evaluate alternatives. And so the horizontal lines represent a decomposition, and vertical lines indicates sub-problems. Just like kind of like down here in the middle, there's a bunch of sub-problems here. And so function trees are exactly analogous, or function structures rather, are analogous to problem trees, and they allow a designer to efficiently, given that the fact they map their function structures correctly, aka the mapping is like a legend. It's like we have here, this is like a legend. This is how we map our problems. And then, or define the mapping for the problems. And then we have a problem, we just kind of purge them or just list as much problems that come to mind as possible. So for example, when we talk about a carrying fastening device, so the dashed lines represents a rejected path and a plain line represents the selected path. So between these two alternatives, we went ahead and chose the near back wheel for a carrying fastening device. And then out of the alternatives, which was a side mount or symmetric, we chose the symmetric route. And then as we chose a symmetric carry fastening device by the back wheel, we then had to arrange how we're going to open it or kind of fix it to the frame, which is through a top vertical or horizontal top back opening, so on and so forth. So then we went ahead and chose a horizontal top back opening. And from here, we decomposed that specific part into two subregions again. So this now carrying fastening device has two more components that is now embedded into this device. So we have a main part and we have a supporting part, and so on and so forth. You can see this can get very extensive. And it's mainly to understand what the problems are, what are they at hand, and how do we go about determining which alternative is the best. And determining these alternatives can be done through a DMM, quantifying it, qualifying it. It could be even earlier in the project charting where we just give the estimation to what it may look like. But then again, it's just nice to have these kind of options so that when if you say, all right, we went this route and it didn't work out very well, we at least can trace back our path to where we started from. So that way we're not kind of just floating in the air with possibilities that we didn't even consider. And so we cut down on time wasted, we cut down on losing production time, etc. So that's a brief intro into problem structures. And these can also be represented as something as like a block diagram, more nodal diagrams or maps, and it can just be words on paper until you actually draw a line or create a legend to associate or develop the relationship between certain parts, processes, or objectives. Another tool that a designer could use is called a morphological chart. And essentially, a morphological chart defines the relationship of what or why and how. And it's conversely, it simultaneously delineates a scale for an end goal, which is the what or why, and the steps to accomplish the end goal, which is the how. And so scope is vastly important, especially when considering systems. And then these tools are useful for determining alternatives as well. So like that functional chart that we had, or functional structure, we have the, or the simple testing, reliable and simple testing device, right? We have a machine that must be safe, which is, how do we get there? So for our machine to be safe, how do we say it's safe? Well, we say it's safe if there's a low risk or injury to an operator. We say our machine is safe if the low risk of operator making mistakes, and a machine is safe if our low risk of damage to workpiece or tool. And so we then want to define the why, and this is where the morphological chart is really powerful, because then we can say it can be a automatic cutout on overload, or which is to say, to reduce the risk of damage to a workpiece or tool, we embed a system called an automatic cutout so that we don't overload the tool. And that's why we do this, to make the machine safe. And then so another thing is like, how do we make a low risk of operator mistakes? You can imagine a box here, where's my pointer? Anyways, oh, there it is, cool. So the automatic cutout and overload for an operator would say like, to have a computer that controls the machine, so that if we have a low risk of operator mistakes, we have a computer that controls the machine that the operator can only use. It'll lower the risk of, and then that system or software can have like software bugs or checks that it implements to check whether or not the operator can do a certain tasks, or it then lowers the risk of the mistakes. And that's why the machine will be safe, because we embedded a system or software that tells the operator what's even possible at this step or not possible at this step by having software checks. The same thing can be expanded for the low risk of injury to an operator. We can say why. Well, another example would be putting an alarm bell. So say if an operator opens a window to a certain manufacturing process, we have an alarm that goes off and shuts down the equipment automatically because the window is now open. This can cause projectiles to exit the operation kind of workspace, etc. And so that's the why the machine will be safe when there's low risk to the injury or operator, by implementing a alarm sound when the window to the workpiece or work environment is opened. And morphological charts don't necessarily have to be lines, arrows, and boxes. It can also be pictures. And what this does is that it helps you to kind of exhaust the configurations at certain heights or certain things or certain, I guess, features. And so the key thing here with all of these problem structures or mappings and charts is that there's always a legend. You always want to have a legend. That way you know what each kind of like denoted icon or symbol represents. And then that way it can also be translated very well to the next person who will be looking at these morphological charts that will be evaluated as well. And so here you can see that this person is trying to evaluate a seating position for a lawnmower. And so you have all these layouts where you have the engine kind of visualized as a block. You have the driven wheels, which is just a circle with dots in it, right? You can have a non-driven wheel, which is a circle with no dots in it. Now we have the operator. So we have that legend there. And we have all the possibilities or the configurations or the configurations that are available or could be exploited. And this can be infinite, of course, but as a designer, you want to kind of eliminate the infinicy by using your intuition, using your common sense. Like, I can't put wheels above the operator because that wouldn't work. The wheels have to be below the operator because we have to be sitting. We're not going to be doing this in a handstand position. Obviously that's where common sense and intuition has to come in and say, all right, brain, let's be more realistic about this. And so, again, morphological charts can be pure diagrams. It's whatever discretion you choose to solve a problem that works best for you. That's entirely it. But then as long as you can communicate it very well. So yeah, that's cool. And so we're briefly going to touch bases on proposals. And so proposals are very interesting because what we said was that they're basically a way to get investors interested, or AKA financial backers, or to crowdsource money, or to leverage certain days of giving, or whatever it may be, any kind of fundraiser or charity event where money is raised. That's where proposals are really strong, because you will then have to take a ill-defined problem. It can be very open-ended. It can be highly detailed to very conceptual, and it has to outline or address the specific objectives and why you're filling those objectives with needs for a purpose or an impact or a solution. And it can be for the mutual benefit, it can be for the exclusive benefit, it can be for societal benefit. And the proposals don't have a discernible format. It's all about visually communicating all of these problems, all these things you're trying to accomplish, all the things that your project will solve into a coherent method where you can leverage, say, advertising space, placement of a logo on a car. It could be like a mention in social media. It could be, throwing shout outs in videos, setting up these tiers to where people can go ahead and give money to you at a comfortable rate, or a rate that's comfortable to them, so that we can then develop a relationship. And that relationship is usually defined by the stewardess, by like stewardism. It could be define a relationship between mutual interest, which is like, say, if we're a motorsport team, we want to go, say, after Red Bull or Rockstar because they fund or they sponsor a lot of motorsport teams in general. Another good example is like, if you're trying to develop a atmospheric water generator, you definitely want to target companies that believe in environmental stewardship. So say like Tesla impact, Tesla kind of is invaluable with environmental impact. Nestle is, I think, one of them. And I guess like the anti to proposals, that although you can find companies that are very strong suited or well aligned with what you're trying to accomplish for a proposal or trying to raise money for, there's also the anti to that, which is companies who need good PR because they went through a string of bad PR. This is also a very dangerous topic to play with, because by telling the company that you recognize a certain weakness, they may feel less eager to sponsor money for a team or for a cause. And so it is, it must be carefully worded to where making something offensive or some result like that is minimized as much as possible. And so this can be used for, again, just to reiterate, for sponsors, investors, or to bid for contracts. And contracts can be through the government, through a public or private interest as well, or a private corporation, a private commercial resident use, anything you can think of. And so the next thing I want to talk about is patents. And what patents are is essentially a way for you to secure your intellectual property. And patents can be stupid expensive. They can range from $500 to $40,000 for a single patent. And companies have like over 1,000 patents. So you can only imagine how much money they've spent on securing intellectual property. But one thing, excuse me, that I'd like to bring up for, I guess, young inventors or young entrepreneurs is that there's something called a provisional patent. And so a provisional patent application is essentially a patent application that can be used by a patent applicant to secure a filing date while avoiding the costs associated with the filing and prosecution of a non-provisional patent application. So provisional patent application is essentially I'm putting a reservation on an idea. I don't have it fully developed yet. I don't know what it entails, what problems it will solve, but I have this idea and I want to secure the intellectual value of it before anyone else can reserve the intellectual value. And typically they're done really well, and they're on the lower end of the cost spectrum, which is like around $500 to $1,000 for a provisional patent. It's about good for a whole year. And again, it allows that person to experiment, find financial backers, and perfect the invention. So yeah. And one thing that I would like to draw a conclusion between is, what does your morphological charts and what does your ideation charts look like? Well, they look a lot like patents. Patents are essentially the discretized or the drawn out versions of ideas and how those relationships are involved. And so patent is essentially what designers have used throughout the recorded history of humanity to kind of preserve these intellectual properties, which could be a product, it could be a service, and it could be like something like the internet. And so these patents are essentially what you've developed over time to say, I'm going to solve these problems. This is how I'm going to solve it with those morphological problem structures, function structures, etc., but in a much more kind of creative outlet. So while also being a financial and, I guess, conventional method to preserving your idea. So that's a brief intro on patents. And so what I would like to actually do now is go through a brief exercise. Cool. So we have another, this is a scale and scope demo for you all. And I'm going to see if I can attach my iPad. All right, let's see if this works. Oh, sick. Wow, that's pretty cool. All right, that sucks. All right, so cool. So as a very high level scale and scope demo, so I would like to have, now that you have this on the screen, let's see. Oh, this is pretty cool. I've never done this before. All right, so we have a typical design process, right? So we have this diamond here, we have another diamond there. We got this big third step, that step, and this step. Liz, since you're the only one here, what do you think this kind of design methodology resembles the most? No pressure, just take a wild guess.
What do I think the method represents?
Yeah, like what? So we have select, initiate, refinement, and prototype and production. What methodology does this represent the most? No pressure.
Was it the diamond one?
Kind of, yeah.
It looks like it.
Yeah, so it is use of the diamond model in a very crude format, yes. But this is actually a agile methodology.
Oh, that makes more sense.
So we spend a lot of time here in refinement because agile was mainly focused on a short-term goal. And agile really seeks to improve through a large number of refinements. And this is why the refinement step was the biggest diamond. And this again can be a diamond, it can be a circle, it's whatever is the best representation form for you to interpret, because exactly this. So if I use a diamond format, right, let's say that if I define the space above the time, so this axis here is time. Anything above time, I say that's my cost of a project, task, or objective. And we're going to say that anything below this line is my priority. Right. So again, a high priority, right, which is here. So we have levels of priority. We have 1, we have a second level, we have a third level, we have a fourth level, and we have a fifth level. So we know that because this consumes all the levels of priority, we are going to say that this refinement step has a priority of 1, because this is where a majority of all levels are. And we can say that, you know, step 2 or step 3, actually, let me get different colors. Ooh, all right. So we're going to say that step 2 and step 3, right, they are kind of on the basis of a 3. So since they're both at the same priority level, right, from this area that we're concerned with and this area we're concerned with, we're going to assign these steps in the design methodology, which is initiate and prototype. We're going to give that a shared priority of 3. So this is a 3 priority and a 3. And then we then determine after between them, which is 2 and which is 3, because we needed 2. But we need something that has a second priority. But because they're at the same level for now, this is purely for just chartering or beginning your project. And we'll say that for, you know, selecting the project and for production of the project, which is here and here, we're going to assign that a priority value of 5. Both of them assign a priority value of 5 because we're going to say these are lower priorities because the purpose of an agile methodology is to put a priority of our time in refining. And then when it comes to production and selection of a project, we're going to say they're about equal. But in actuality, we know that selection will probably be 5 because that's probably the easiest thing to do. And production is going to be a 4. And this is completely arbitrary at the moment. I haven't assigned any quantification or qualifications. We're just doing this to begin the project. And you know, we can use function structure. We can use a morphological chart as this scope and scale will change over the project, or they will evolve, right? So let's give ourselves, let's say prototyping is a higher priority. So I'm gonna put that at a 2, and this is gonna be our 3 to initiate the project. And then a priority for us would be 1, which is here, right there. So now we defined our priorities. And now how do we get an estimate of time? Well, that's very straightforward. We can say that here, so we'll make time in red. So we know our time scale right off the map, or right off from viewing this. So we know that time literally just follows this kind of path here. It changes there, changes here, but it's constant, right? And so we know what our time values are. And then because we're within each domain or shape, right, we have these time intervals that we now are bounding ourselves towards. And so here at this last step, this should be to where we're, you know, deliverable. And here we have, in this first time bound, we'll say that to select a project, it'll take like maybe 2 weeks. So we'll assign it to WKS. We'll say that because, and that's based on relatively to our priority scale, which was given a 5. And then say, because we have an initiation project, we want to get this done with a higher priority, we say we'll bump this down to a 1 week. Or rather, it's gonna be a 1 week because it's a lower priority, so we don't need to put that much time on it. And then for refinement, we'll say that'll take about the majority of our time. So we're gonna give ourselves a 12-week scale to complete this project. So we have 12 weeks to complete this. And say we want to spend most of our time in refinement. We want to find that after we've developed what our priorities and scales are for prototype and production. So we want to give ourselves the most time. So say we estimate that we're going to take about 4 weeks to produce something or prototype something, and it's going to take us, right? Actually, take that away. And so we actually know what our timescales are by the length of the domain that we're working in. So since we're going to keep it easy, since initiation and prototype have the same length, we're going to say they're both equally going to take 2 weeks. And then say here, this is going to take 4 weeks. And then on production will also take 4 weeks. So we have, that won't actually work because we're going to go over the 12 weeks we've allotted ourselves. So I'll say that's 2 weeks. This would be 1 week. There you go. So we've used up, to kind of backtrack here, right? We have 12 weeks in given an agile. So that's our total allotted project time. We've then estimated that for selection and production, it's going to take 2 weeks each. And we've also said that for initiation and prototyping, we'll take 1 week each. So we've already lost 6 weeks. So this means we've allotted ourselves 6 weeks for refinement, right? And that's because we developed the fact that we're going to be spending more time here in the refinement process, and then less time in the initiation and prototyping process, and then somewhat arbitrary more time in selection and production. And again, these timescales are totally dependent on what you think, based on what your team capability is, what your management capability is, what the overall intended scale and scope of the project is. Because, I mean, this can get extremely crude. And so what we've done now is that we've assigned a scope, or rather a scale. Right, so we've assigned a time scale here. Excuse me. We've assigned a priority scale to these tasks, or these certain steps in the tasks. And now we need to understand scope. So we say that scope is the, I guess, the planning or project scope as to how much time or what is relevant during that time. So scope is literally the area in between, which I will draw here. So this is your scope here. This is your scope here. Again, this is a scope here, so on and so forth. But one thing I want to highlight here is when we have scopes, I'm going to just erase all this. So scope is really important because we have an overlap or transition point where certain steps along the way have to interact for you to have a successful outcome. And this is purely dependent on the project, but to give you guys some overview. So some scope that we're going to be defining here. Ooh, that's a bad color. Ooh, even worse. All right. So we're saying scope here is essentially this area between each kind of step. And we also have these interjections here, which are, can be big or small. And essentially, right, we said that this was going to be cost and this was going to be time. And so now we've given ourselves a scope to how much cost and time will take at that scale of a step within the project. So let me repeat that. The scope is the assessed cost and time scale for a certain step within a process. So if I had said, all right, we're going to spend a lot of time here in refinement, but I then say, well, or someone comes along and says, well, to select the project, how do we know we're selecting the right one? So then our diamond goes from a shape that looks like this. Oops. From a shape that looks like this to say, all right, it's going to take more time, which is on, no, more cost. Yeah, cost here. And we're going to say this is priority. So we say there's a higher priority in selecting the project. Okay, so, all right, then diamond may look like this. And it should take less cost. So we'll keep the top shape there. And so now we've increased the priority of selecting a project because we've now extended that line down, but the cost of it remains the same. So the scope changes, right, as we've changed the scale. So now we've added more area in terms of priority because we think selecting the project would take much more time, like right here. We've then changed the scope. So anytime we change how much something has a cost or a priority towards a certain step, you then have to allocate that scope that has to be changed for that step. For example, if you had something in a prototype and the cost of prototyping, you know, if it took us out here, which is outside of our main scope or project scope, we say that anything in this region here is out of scope or is not feasible. Why? Because it either costs too much, the ideas that we had generated during this step isn't feasible, and it should not be undertaken because it's literally out of scale and scope. So avoid this area, and this is like your cutoff line here. And so you want to stay bounded within here. So that is a brief way to kind of view and project estimate for your Gantt chart. So that way you can define the timetables that you have. And again, I didn't bother expanding the amount of time that changes. I only wanted to focus on costing and priority and how that changes your scope so that you can say whether or not we should do this, essentially. So let's move on to the next item here. And that is, oh, problem structures, cool. Oh, no bueno. So let's work on problem structures. So for example, we're going to begin with saying we have a need, and whatever that need is, we're going to say we have to define a certain amount of features, we'll say 3 of them, that must be included into the design that we designate will make a successful manifestation or answering of that need. So say that our problem structure is, what's a problem? What's an everyday problem? Let's say traffic, right? Traffic is an everyday problem. Ooh. So like I had said earlier, you basically just take your problem, which is traffic, right? And we can say all these problems about it, right? There's, there's congestion, right? There's an environmental impact. And we can say that traffic has it adds stress.
Do crashes count, or are they a result of congestion?
You know what? That's a problem too. We'll put that there.
Mhm.
So we're just associating the relationship with traffic and all the things that we can identify as how do we solve traffic. And so we have the subset of problems to the overall problem, which is traffic. So now let's draw some notes to these. Basically just circling them. And we've now encompassed our main problem into a subset of smaller problems. So now that we have this problem structure, let's try and define, let's work on environmental impact and crashes for the sake of time. So we'll say for environmental impact, right, there's pollution, there's material sourcing, aka refinement of oil. We'll say oil refinement. There's crashes. I'm sorry, what's that?
Land use.
Land use, that's a great one. Any others? Yeah, don't worry, this is only initial thinking. So for crashes, when you suggested that, and what do you think it contributes to crashes and how does that affect traffic?
Human error.
Right on the money, human error. What else? That's a very general
tightness
statement.
of lanes too.
Oh, right. Topography of roadways. And right, there could also be misinterpretation of signage. Right, that could also lead to a crash. So now we say that for all these things that could be what contributes to crashes and what contributes to environmental impact, is we've now have developed a hierarchy to say, if we can figure out how to solve pollution, how to figure out material oil refinement, if we can figure out how to subvert land use, we can then diminish environmental impact so that way our traffic can be minimized, the problem of traffic can be minimized. Or we can then also say that crashes which contribute to traffic can be minimized by minimizing human error, improving the topography of our roadways, or decreasing or minimizing the misinterpretation of signage. And so one thing I didn't get to do because of the space I'm working with, but I did say that these kind of scales here, so we have this length or this vector, and we'll say that this length of vector is equal to say like 2 months to solve, so 2m, and then because these are all equal, we're going to say it takes 2 months to solve each of these problems. And we know traffic won't ever be solved in 2 months, so we'll just go with 2 years for each instead. And then to say for each of these vectors that we also assigned here, between the problems, like here, so for us to work from here and here, which is to encompass everything, right? We're going to say that takes, a year. And then each of these three can say, well, we'll take up to 4 months to solve at each of these intervals because they're all equally identical-ish. And so we say it takes 1 year to solve all the problems of land use, material, and pollution to solve environmental impact, which takes 2 years to solve, and finish for solving traffic. So we've assigned ourselves a time scale between these problem structures. And then we also say we've identified what these problems may have been. So that's what all these circles are for. So our circles are us identifying the problem, and then defining the problems to solve for the need, which was traffic. And so we then have a greater subset of problems to achieve in order to accomplish a minimizing of traffic, which is human error, topography, or pollution or land use. So again, just to reiterate, we have a need, which is traffic. We have its first primary problems that we've identified to be congestion, stress, crashes, and environmental impact. And those are the whys. We have a traffic problem. And so how do we solve these problem structures? Well, we take a look at pollution, we take a look at material, we took at land use, and we take a look at crashes, we take a look at human error, the topography of roadways, and misinterpretation of signage. And that's how we solve the problems that encompass traffic, which is a need. And we then assign those timescales with these length of vectors between the problems and the solutions, or the what's and whys and hows. And we'll say it takes 2 years to solve the relationship between stress and congestion to solve traffic. And we'll say it's going to take 2 years, etc., for everything else. So that's a very crude example to a problem structure. The next thing I would like to kind of briefly introduce to you all is a decision tree. So, there we go. So, let's get into this. And so going on the basis of solving traffic, right, now we have to decide what problem or how we go about solving those problems. And we kind of did that. So let's take that problem tree and then break it up into a decision tree, right? So we wanted to solve traffic. We then said that at this level, to solve traffic, there is congestion that we have to figure out. There's environmental impact, which I'll abbreviate to EI. Then we have crashes, and we also have stress. So we're going to kind of neglect these two for now, for the simplicity of time. And we're going to say for environmental impact, we had said that what affects environmental impact is that we had a pollution, we had materials, and we had land use. And then for crashes, we said that, blanking on this one. So crashes, we said there's human error. So human error. And we'll say that there's topography. And then we'll just say here signage. And so now we need to decide which ones do we choose to pursue in terms of research, exploring, and finding possibilities to trace back to solving traffic. And we've already assigned ourselves a time scale, right? So we say that this length here is equal to this length here, equal to this length here. Or actually, that doesn't even work. So the timescales, I guess we'll call here. Right, we said that would take about 2 years. And we said that this timescale here, this would take 1 year. And then we said here at this time scale, this would take 4 months. And you imagine these lines kind of trickling down like this. And to solve these problems, it takes 1 year. And to solve these problems, it takes 4 months for each, right? So this kind of makes sense, right? So for me to solve environmental impact to solve traffic, right? If I might allocated 2 years, and here for environmental impact, I'm given 1 year, and I have these 4 months allotted for me for these 3 solutions. And then for crashes, I have these 3 solutions, which is human error, topography, and signage, allotted within the 1 year for crashes, which is the total 2 years we've given ourselves to solve the need of traffic or the problem of it. And so now now that we've assigned the expected time value, so red equals the expected time value, time scale. Now we need to evaluate which ones is the higher priority. And we say that pollution is a big aspect of it. Obviously, all of these are big priorities, but how do we differentiate between 3 of these alternatives? And so that we assign ourselves a weighting factor. And what weighting factors do is that it says that for environmental impact, we say that out of a scale of 1, so we'll assign, and this weighting factor can be broken up and scaled again, but I want to focus on the solutions that we've kind of conjured here. So to equal a weighting factor of 1, so it all must equals 1. And this is also a weighting factor, which I'll highlight as WF. And so we've given ourselves a weighting factor of about roughly 1 for crashes and environmental impact. And say for pollution out of a scale of 1, we say that pollution is probably our highest priority. And I would say land use is probably the second priority and materials is the third. So we'll give ourselves this value. We'll say that's first and we'll say that's second. And we'll go ahead and prioritize the human error, topography, or signage. And so we say that human error would be number 1, I would argue. Again, this is all very subjective. Unless we actually pull in data, then we can get a better definition, priority, and weighting factor. But for now, let's keep it simple. Let's say that topography of roadways is 2, and that signage is 3. So we've now assigned the priority, which is in turn, we've then assigned the weighting factor. So out of a scale of 1 for pollution, materials, and land use, this doesn't have to be equally distributed. So for example, I say that pollution is 1, I'm going to give this a 0.5, right? There's a lot of things that lead to pollution that determines from like the conceivability of a product or the conceivability of traffic to its impact. And we say that pollution is a 0.5 on that scale. Because materials is a very low priority, I will assign a 0.1 value or weighting factor to materials. And then for land use, right, that we know that 0.5 is consumed and 0.1 is consumed. All that's left for land use is 0.4. So that is our weighting factor. So now we have a total of, right, we have 0.5 plus 0.1 plus 0.4. And this is equal to 1 for our weighting factor of EI. Right? And let's do the same thing for crashes. We're going to say human error is 1. So let's say that this is a 0.5. And then we have topography and signage. Now we said that the priorities are 2 and 3, but we think that they're equally, they have a both equal weighting factor in terms of crashes because topography of roadways and signage are intertwined, right? If we have signage, if we have roadways, there must be signage, right? So we'll assign them an equal weighting factor, which would be 0.25, right? And again, that equals to roughly a weighting factor of 0.1, so 0.5 plus 9 times 2. And that is roughly equal to 1, which is the weighting factor for crashes. So in this decision tree example, we have just broken down what our expected time value is, which is in the blue, or in the red rather, I'm sorry. And then we have assigned our qualitative scale, excuse me, which is the weighting factor, and that's our priority as well. And so we know that we're going to be spending a lot of time in pollution because it requires it has the heaviest weighting factor for solving environmental impact to solve the need for traffic. And so designers should probably think about this in the way it's interpreted and how it's read back, because it's very strong for you to understand what you're trying to achieve. And that way it's also a sanity check for a designer to say, okay, yeah, so if I have more emphasis on human error is what I prescribe the problem of crashes to be to solve the need for traffic, then yes, I can say that human error is about 50% of the reason for crashes that lead to traffic, which is a big problem. I feel like when I was back home, there's like a crash or morning crash like every morning. It was awful because our roadways topography and signage is awful. So all very, very mutually inclusive of each other. And we've assigned a time scale and we've assigned a priority to them, AKA qualitative and quantitative measure for prescribing the initial project charter, which we would then use to make a Gantt chart, which would go back to something like this, and we've defined our timescales. Now I want to go into the last exercise for us today, which is not working. Why? Cool, it is working. So a DMM is basically a decision-making matrix. And what it is it's used to filter out design options and compare it to doing nothing, or similarly like an off-the-shelf product. So typically in Formula SAE or VMS, or FSC rather, is that you either have to choose to design something by hand or by a student, or choose to buy it off the shelf because you're either trying to balance cost and priority for what time is being spent for, or money is being spent for. Again, those are reversible. And again, it must have a defined description of requirements and a linear rating system to quantify this said thing, which is those weighting factors we just went about. And to then again go about deciding how we make those decisions for a certain step or process, we need the objective for that, which is what I was repeating in the previous example. We assigned a weighting factor. Parameter is how we, I guess, like the units of it's just basically the units of whatever we're trying to measure. It could be relative, or it can be empirical, or it could be length, or whatever. We have a magnitude of that scale, which is it's the qualitative thing to say, this product is very good for that, or this product compared to this does terribly when doing this certain function. Or another way to say magnitude is like, this product beats my expectations. It went above and beyond my expectations. So when we say those qualitative things, those things are also assigned a quantitative measure or scale to give us justification for that reasoning. And so score and value, again, is just the score you receive from multiplying it with this. You get the score from multiplying the magnitude scale. The score and the magnitude are the same matrix, and you multiply that by the weighting factor to get your value. And so what that looks like for a cool. So what that looks like for a typical vehicle, or for any component rather. So just like we have powertrain and we have a suspension model. Let's see if we can save this. Cool. So, for example, why this is also kind of rather difficult. Ooh, that's irritating. Un minuto. Cool. So, right, so we have an objective for our powertrain. So we have our need here. This is our need. suspension. So we then define goals for a certain need, or like with us in red, and those little goals or requirements are also known as objectives. So we have those here, right? They want to be in your left-hand most column all the times. And just to give you some background, right? So here we have the parameter, again, oh, that's a pencil. So we have parameter here, and these are just, again, like units of measure, if anything, right? And then here, what we're actually comparing is all of our alternatives. So we have right here our first alternative, which is broken down right here. This is our first alternative for powertrain and suspension. Here's our second alternative that we're bracketing. And then here's our third alternative. So we have alt 1. It's a terrible color to write in. So we have alt 1 here. We have alt 2. And we have alt 3. And so for each of these alternatives, which would be OEM straight, independent front and rear axles, or engineered straight axle, right? These are all your alternatives for powertrain, and for suspension, for example, we have the OEM, we have the independent, or we have solid front and rear, all adjustable. And you'll notice, like I said, right, we always have to compare the off-the-shelf method or the do-nothing method, which would be this one, the OEM axle straight, or the OEM axle setup front and rear. So these are your controls, you know, what you're comparing them to. This is everything that bases your decision off of. And you can see that sometimes when you have just to kind of prelude here, is that you have an alternative like alternative 2 for powertrain. You can see that the OEM resulted in a greater score than the actual alternative proposed. And this is totally fine. You may have someone that proposes an alternative, but then you go back at your objectives and say, does this alternative meet our objectives? And then this is how we define the magnitude of the score here. But that's a little forward thinking. Just wanted to bring that to your attention. But without further ado, let's get into the actual process here. So again, just to recap, I define the needs, which is this powertrain and for suspension. Right, we are comparing 3 alternatives, which is found here. These 3, we have these 3. And then the alternatives we're comparing, what we want to compare them against is the objectives that we've set for ourselves right here. And so for powertrain, we said that the powertrain must complexity should be, if it's a highly complexive or it's highly complexive, it'll get a lower score. But if it's very simple, it should get a higher score. So for example, the OEM axle for complexity, because it's simple, and this simple was determined from the fact that it's already built for us. We don't have to do anything, right? We just take what's given off the shelf and we use it. Now, when we say we move on to the alternative for front and rear axle, we gave this a magnitude score of complex. And that was because of the fact that independent front and rear axles are great, but they're also very difficult to implement because you have kind of difficult to implement. And then versus the engineered straight axle, which is just a little a beefier version of the OEM axle, which is a straight one as well. And this also got a relatively simple score, which is good. And that's why I received an 8. And so on and so forth. You go ahead and go down all these objectives and you assign them to the alternatives. And so we also have this thing called the weighting factor. And this weighting factor was determined from what is our priorities. So again, this is like priorities to us in terms of the objectives, right? So on a scale of 1, 2, 3, 4, 5, 6 of them, we said that this has the greatest priority, while this has the lowest priority. So our objective, our highest prioritized objective was complexity, and our lowest prioritized objective was weight. So we say that weight isn't necessary for us, and we can say that customizability isn't a factor for us. We also say that cost is not a factor to us because one, we may be a company that has a lot of money to spend. Two, customizing isn't targeted towards our customer base, and weight isn't relative because it's going into something that's already heavy. And those are the arguments or justifications that could be prompted. And again, I sound very subjective, but again, this could be an actual project, and no project is the same. But in terms of this is in terms of like a mini Baja kind of car. But if we were doing this in terms of a Formula SAE, all of these kind of objectives and priorities would be kind of flipped in a sense. Saying that weight would be a big thing for powertrain to keep low because you want a high power to weight ratio, etc. I don't want to babble on too much. And the same thing can be applied to the suspension. So we had our priorities that we rated here. We said that durability was the highest one. And then we had 1, 2, 3, 4, 5, 6. Well, those weighting factors are out of order, but you get the drift. And so, so cost and complexity would actually be here at the bottom. So now that we've defined our objectives, we've talked on a weighting factor, and we have a unit of measure or the parameter to what we can measure it with, or AKA the M in the SMART goal analysis. And we have to say whether it's attainable or realistic. And so that's where we determine the magnitude from. Is it realistic, and is it achievable or attainable? And again, these magnitudes are just qualitative definitions of what we say. Like we said that the customizability of a straight axle is averagely customizable, or if we were to build our own, which is alternative 2 or alternative 3, the customizability factor is excellent because we're designing it ourselves, whereas something off the shelf, we don't get the chance to design it, so we have to take it as is. For suspension, for example, we have a like an OEM axle setup versus independent front and rear axles, and solid front and rear all adjustable axles. So for centrifugal handling, because we take the OEM, we denoted it having an OK magnitude value. And whereas if we were to design something ourselves, we could give it a slight increase in performance of centrifugal handling. And so we then determine how do we go about to picking alternatives. So to pick our alternatives, we say for each alternative, we give it a magnitude. That magnitude has a corresponding score. So if it's a simple, it's a 10. If it's extremely complex, it receives a 1 for powertrain. And we then assign those scores given to that, and then those scores are then multiplied by the weighting factor. So we have a 10. If we're looking at powertrain, we have a 10 score with a weighting factor of 0.25, which achieved a value of 2.5. And because that was the highest score on the highest weighting factor value, this has to be a 2.5. And to break it down again, this is roughly 1. And then this scale, because our scale is out of 10, right? Our highest number is 10. The maximum result that we can get for any product would be 10. So we can get a 10 there, we can get a 10 here, or 10 here. So that's our maximum score that's achievable. No product will ever get a maximum score because there has to be trade-offs. But if you have anything over than 10, then you had an error in setting up your table and whatnot. So you can see that the OEM straight axle received a 7.5. The alternative 2 for powertrain received a 6.2, while the third alternative received an 8.6. Obviously, from the result of basing your objectives based on the weighting factor for your objectives, you would then know if you're in powertrain to go ahead and choose alternative 3, because that is the alternative that resulted in the highest result. And you can go ahead and choose that alternative when justifying your decision and presenting it in terms of proposal or presentation or public speaking, technical reports, whatever it may be. And so that's a rough introduction to DMMs. And let's see if we can go back to the presentation. Oh, all right. And so to cap it off, for DMMs is to ensure the objective can be qualitatively and quantitatively defined within a single term or hyphenated terms thereof, like cost, manufacturability, viability, simplicity, coherency, compliance, durability. There's literally so much words. And if you were to, and a good notion for you to define a quality is usually when a word, if you look it up, say like viability, the definition specifically says it is to the degree of this. So for manufacturability, it just be like to the degree of manufacturing X, Y, and Z. When a definition for a word literally has the phrase to the degree, that literally is a signal for you to choose it as a single term to quantitatively or qualitatively define an objective and its magnitude. And those things have to be kind of equally masked there. One thing you need to ensure is the magnitude scales are equivalent. So again, I iterated this in the beginning. So either the scales are out of a 5 or a 10, but not a combination. Otherwise the relationship breaks. And you must ensure the objectives can be measured for design justification, which is to say, we decided this because we said these alternatives do not satisfy our objectives, thus our justification for choosing this alternative. So I went a little over time today, but I hope that was enough information. I kind of breezed through the end bit there. If there's any questions, comments, or concerns that you'd like to talk to me about, or things you want to be more in depth, you can go ahead and leave a comment in the design channel, or go ahead and ping me directly, and I'll try my best to answer it as soon as possible. But thank you all for coming today, and I wish you all the best of your week.